Hello, my name is Loshini and welcome to our Chemical Engineering Lab 2 group presentation. We from Group 1D has done the experiment about kinetic modeling of hydrolysis of acetic anhydride at higher temperatures using adiabatic batch reactor in pharmaceutical industries. To start with our introduction, acetic anhydride is a colorless transparent liquid with a distinct deep vinegar smell. And did you know that when water is added, acetic anhydride interacts at a fast rate to produce acetic acid? This reaction could be quite exothermic and intense. Most publications define the reaction rate in acetic anhydride as pseudo first order since majority of the study has been done in a significant excess of water. In each experiment, the adiabatic experiments provide data on the rate of production of acetic acids against several temperatures. In our experiment, we have done two parts where acetic anhydride hydrolysis in excess distilled water, which is a dilute solution, was differentiated with the hydrolysis in excess anhydride solution under adiabatic conditions. Our experiment revolves around the kinetic modeling of hydrolysis of acetic anhydride at higher temperatures in an adiabatic batch reactor. There are three objectives in our experiment today. The first objective is to determine the effect of hydrolysis of excess acetic anhydride under adiabatic conditions. The second is to prove that the hydrolysis is a first-order kinetic model. And the final objective is to find the relationship between the kinetic parameters of the reaction between acetic anhydride and methanol. Moving on, for the market analysis, we first analyzed acetic acid. The common types of customers are Asia-Pacific countries covering China, Japan, and India, while the market size in the year 2020 is USD 9.3 billion, and the market demand is predicted to grow with the annual growth rate of 4.5%. For antibiotics, where the common ingredients are acetic acid, the customers are Asia-Pacific countries as well with 45% market share, and the market size is 41 billion USD, and the market demand is predicted to grow with a 4.5% to the year 2028.
For the upstream, 3 blending tanks are used to contain a nutrient medium, glucose, and act as a seed tank for growth of Penicillium, Chrysogen, and fungi. The medium and glucose streams are mixed uniformly and fed for decontamination under high temperature using batch sterilizer. The two streams then enter a batch tank bioreactor, and the fungi culture from seed tank is inoculated for fermentation. Penicillin 5 is extracted by fungi after 40 hours. The process is run for 7 days until pH reaches pH 8.0. Removal of biomass and fungi from penicillin solution is then carried out by rotary drum vacuum filter. Remaining solids are then acidified to maintain product activity and added with organic solvents to dissolve the salt. Solids are recrystallized and washed before filtering them out from the solution using basket centrifuge. The excess acidic water from centrifugal extraction is neutralized before release. Finally, moisture is removed using fluid bed dryer. The list of equipment used starts with the continuous third tank reactor or CSTR. They are used as blending tanks. Next, a mixer is used to mix different liquid feed streams uniformly. Then, a batch sterilizer is used to remove microbial contamination by high temperature using steam flow. The main unit is the batch tank bioreactor for fermentation. The unit has stirrer and bubble columns for uniform mixing of glucose and also comes with temperature and pH controllers. There is also a rotary vacuum drum filter which has rotating drum with a clog and vacuum where solid is removed as a cake layer and moisture is removed during dewatering. A D-stack centrifuge removes smaller heavier solids from lighter liquid towards the outer wall by centrifugal forces of rotating stacked discs. The basket centrifuge filters work by similarly using a rotating drum with perforated walls. A fluid bed dryer removes moisture from the solid penicillin 5 salt by blowing hot air from the base to fluidize the solid and dry efficiently. Based on the experimental setup diagram, a negative temperature coefficient thermometer is attached in a thermos flask batch reactor. This thermometer is connected to a Clarity data acquisition system. This is finally connected to a data processor running MATLAB 2012A.
In part A, we study about the hydrolysis reaction with excess of water under 3 different temperatures, 305, 310 and 328 Kelvin respectively. The result for these 3 temperatures shows similar trend in these 3 different graphs below. First of all, graph of mass of water versus MCP over UA is plotted to determine the heat transfer coefficient of the process. From the graph, the value is identified as 0.00209 per minute. Next, the temperature time plots in the MATLAB simulation can be used to determine the initial temperature, maximum temperature, and difference of temperature delta T. From the graph, the experimental cooling process decreases slowly and shows similar trend as theoretical adiabatic curve. Besides, the graph of concentration versus rate are plotted to determine the average rate of reaction, negative RA from calculation of first derivative at different time intervals. By using kinetic values from the temperature time plots, Arrhenius plot and different temperature can be plotted to calculate the heat of reaction, delta H. The equation at the right side are generated from this graph and can be used to calculate the specific rate constant by substituting temperature into them. The R-square value for this graph are around 0.99, which shows that the results are having high accuracy.
As for Part B, excess acid anhydride water reaction was studied, and similar procedures were utilized as in Part A. Firstly, a nonlinear regression analysis was performed adiabatically with the initial temperatures of 286.8 K, 293.6 K, and 304.5 K respectively, to obtain the heat transfer coefficient, where all three graphs show similar trend. With that, the experimental curves were determined, and the regressed line data have been corrected using the equation as shown, where the temperature time plot was generated through MATLAB simulation software. Secondly, with the concentration time plots, the average rate of reactions for all the experimental runs were determined, and it is observed that the trend in the concentration plots shown that reaction in Part B follows second-order reaction processes. All concentration rate graph was done under 320K, 325K, and 340K respectively, and thirdly, heat of reaction then is determined using the Arrhenius plot using the equation shown. All three Arrhenius graphs show the same trend.
For experiment A and B, the obtained observations are new and surprising as stated by the article. First, we will look into the MATLAB graph. For the Part A, the experiment cooling process decreased slowly, which show the similar trend as the adiabatic curve in the MATLAB simulation, while for the cooling process of Part B, the temperature decreased exponentially after the temperature peak for the first two graphs, with the initial temperature of 286.6 Kelvin and 293.6 Kelvin respectively. However, for the third graph, with the initial temperature of 304.5 Kelvin, show that the temperature decreased almost linearly, which is indicate that the behavior of the cooling process does not follow the trend of adiabatic curve. Next, I will discuss about the rate versus concentration graph for both parts of experiment. As seen from the three rate versus concentration graph of Part A, the trend from the graph shown that the rate is directly proportional to the concentration, while for Part B, the trend from the three graphs show that the similar trend, which initially the rate increased gradually with concentration, then increased sharply once concentration has crossed almost 50% along the x-axis. From the Arrhenius plot of hydrolysis process for Part A, the heat of reaction is 53.36 kJ per mole, negative 53.44 kJ per mole, and negative 53.51 kJ per mole, which are similar to the theory from the article. As for the heat of reaction in each of the Arrhenius plot in Part B, it is obtained at negative 53.92 kJ per mole, negative 60.71 kJ per mole, and negative 60.99 kJ per mole. From the obtained heat of reaction for both parts of experiment, we can observe that the heat of reaction obtained in Part B are smaller than the heat of reaction presented in experiment Part A. For the safety precaution, we must make sure that PPE are always worn throughout the laboratory session. Besides that, all cables are plugged into appropriate socket before main power on. And before we switch on the heater, we will always make sure that it is full submerged into the liquid to avoid any damage. Moreover, the stirrer is always make sure that it is secured properly and the excessive load is avoided to the electrical motor. And lastly, for the safety precaution, the unit, including the tubing and the fitting, were inspected periodically for leakage. Next, for the safety and maintenance, any liquid from the reactor were drained off and were disposed immediately after each experiment.
The kinetics of the reactions acetic hydride excess water excess acetic hydride water was modeled as a function of temperature in a diabatic batch reactor, using a negative coefficient thermistor as a measuring device. From the results, we can observe the acetic hydride excess water process at 1 to 10 mole ratio. The process remains as a first order at higher temperatures up to 366 Kelvin with activation energy similar to the one at 298 Kelvin. Excess acetic hydride water reaction was observed and analyzed that they follow a second order kinetic with respect to water. The activation energy is approximately 37.1 plus minus 2.8 kJ per mole. The heat of mixing is assumed to be negligible and is not taken into consideration during the heat of reaction calculation. This study shows that the two processes studied appear to be completely different processes and may have completely different reaction mechanism pathway for acetic acid production.